Sometime last year, a document attributed to Huawei's Semiconductor Research Division described a fabrication architecture called LogicFolding. Two logic dies, stacked, patterned with 193-nanometer immersion light, no extreme ultraviolet machine anywhere in the supply chain, and attached to this architecture, a node label the industry had reserved for processes years beyond what that kind of light can physically resolve on a flat surface, 1.4 nanometers. The believers read it as proof that Chinese engineers rewrote the rules of advanced logic under sanctions, reaching a density milestone that TSMC and Intel are still chasing on their public roadmaps. The skeptics read it as a marketing label applied to a clever stacking trick, where 1.4 nanometers here means something categorically different from 1.4 nanometers anywhere else. Both sides are citing the same document. The rounds below weigh the evidence and call each one. 4 rounds decide this: the density claim, the cost and yield rebuttal, the usability question, and the node naming dispute. Then a verdict on what Huawei actually proved and what it did not. The LogicFolding disclosure is the physical exhibit that both sides are cross-examining. It is not a chip shipping in a phone or a data center today. It is a disclosed method, a specific architectural description of how stacked dies processed on existing tooling can reach a stated density target. Every round turns on what that method demonstrates and what it leaves silent. The disclosure enters round 1 as the bullish exhibit, becomes the skeptic's primary target in round 2, is stress-tested for real-world usability in round 3, and defines the entire node naming dispute in round 4. In the verdict, it is simultaneously more and less than advertised. Keep that tension in mind across all 4 rounds. The bullish claim in round 1 is straightforward. LogicFolding stacks 2 fully processed logic dies, connects them with interconnects fine enough to treat the vertical combination as a single functional tier, and applies self-aligned quadruple patterning on 193-nanometer immersion tools to achieve what the disclosure characterizes as roughly 55% higher transistor density compared to a reference planar process. Under export controls that cut Huawei off from the Dutch manufacturer's extreme ultraviolet systems entirely, engineering a density gain of that magnitude on legacy tooling is a legitimate result. The engineers did not cheat physics. They rerouted around a physical constraint using architecture, which is a different kind of accomplishment than bypassing the constraint directly, but it is an accomplishment. The counterclaim deserves equal air. 55% density improvement over which baseline? The disclosure does not name a peer process node as its reference point. If the comparison is against Huawei's own prior immersion light node, rather than against a leading-edge extreme ultraviolet process from a major foundry, the gain starts from a lower floor. A genuine 55% improvement over a trailing reference may still land well behind the density of a current generation extreme ultraviolet process. The number is internally consistent and possibly accurate, while being framed in the most favorable possible direction. The evidence on round 1 is actually fairly settled on the technical fundamentals. Self-aligned quadruple patterning on 193-nanometer tools is an established, independently understood technique. It multiplies pattern density through repeated deposition and etch cycles, rather than through the wavelength of the light source. The density gains it can deliver are real and have been demonstrated in production at multiple foundries for memory applications. The stacking method Huawei describes, bonding 2 logic dies and routing signals vertically between them, is architecturally similar to approaches that leading foundries already use for advanced packaging. Neither technique is invented for the occasion. The combination of the 2 in the LogicFolding framework is the claimed innovation. What has not happened yet is an independent fabrication lab publishing a teardown or yield analysis of a chip produced using this method. The density figure comes from the company's own disclosure. Reports suggest the architecture is real. The exact density gain relative to third-party nodes at competing foundries has not been independently confirmed by anyone outside Huawei. Round 1 to the bullish side, narrowly. The engineering is real, the techniques are established, and the density gain is not invented. The reservation is the unverified reference point. Real gain, uncertain magnitude. Round 2 is where the skeptics land something solid. The bullish frame here is that stacking logic dies is already in production at leading foundries for premium products, and every new process architecture launches with worse yield than it eventually achieves. The question, on this view, is whether the architecture is scalable in principle, not whether the first disclosed version ships with perfect economics. Manufacturing maturity is a solvable problem. The architecture came first. That argument is real, but it undersells what it is conceding. Stacking two logic dies and treating the result as a single equivalent node creates yield multiplication. If each individual die yields at 80%, the stacked pair yields at 64% before bonding losses are counted. The LogicFolding disclosure publishes no yield figure. It does not quantify the thermal budget of running two active logic tiers in close vertical proximity. Heat is the constraint that has limited three-dimensional logic, stacking more than lithography has, because the buried tier cannot shed thermal energy the way a surface die can. The disclosure does not address the cost of the bonding process itself, which at the interconnect pitch is required for logic. Equivalent density is expensive and equipment-intensive in ways that do not scale down as cleanly as photolithography does. Architectural density equivalence achieved through stacking is not free. The cost is just moved off the lithography line and onto the bonding and thermal management line. The disclosure proves the concept. It does not prove the economics. The evidence on this round is clear in direction even where exact figures are unavailable. Yield multiplication and stacked die configurations is a well-documented manufacturing challenge. It is the primary reason three-dimensional memory stacking, which layers simpler memory cells rather than complex logic, took years to reach cost parity with planar memory after its architectural debut. Logic stacking is harder than memory stacking because logic dies are less regular, more thermally active, and more sensitive to interconnect delay. Removing heat from a buried logic tier is an active research problem at every major foundry, not a solved one. Reports from industry analysts suggest that no high-volume logic product has been manufactured using face-to-face bonded logic stacking at the interconnect pitch that would be required for the density claimed in the LogicFolding disclosure. The approach is that leading foundries use bond logic to logic at pitches and within thermal envelopes that position them as advanced packaging solutions rather than node-equivalent density solutions. Huawei's claim that LogicFolding achieves node-equivalent density through stacking is, on current public evidence, unverified at production scale. Round 2 to the skeptics, and it is not close. The disclosure proves the architecture on paper. It does not prove it in yield, in cost, or in thermal management. Until a production chip is analyzed by an independent laboratory, the gap between the disclosed method and a manufacturable product is real and large. Round 3 asks a different question. Even if the density gain is real and the economics are murky, does the result matter in practice for the market where Huawei actually competes? The bullish argument here is pointed. A density gain is a density gain regardless of how it was achieved. If chips produced using LogicFolding pack more transistors into a given footprint than Huawei's previous generation, those chips are more capable. The artificial intelligence accelerator market, where Huawei competes most directly against NVIDIA's export-restricted products, rewards density because more transistors mean more matrix multiply units and more on-chip memory bandwidth. If the method works at any yield above 0 for a premium product, it changes what Huawei can offer domestically. Under the current export control regime, Huawei does not need to beat TSMC's leading node globally. It needs to advance past its own prior ceiling for customers who cannot legally buy the restricted alternative. The counterclaim is that the domestic competition frame has real limits. A chip that achieves density through stacking at significant cost and yield penalty is expensive per transistor. Expensive per transistor artificial intelligence compute loses to cheaper alternatives on total cost of ownership even in a captive market because the customers are running large training clusters where per unit economics multiply across thousands of accelerators. If LogicFolding chips cost substantially more per effective transistor than a chip fabbed at a leading foundry, the architecture's practical impact depends entirely on a cost structure that has not been disclosed. The captive market is real. The captive market is not infinitely price insensitive. The evidence on round 3 is split between what is confirmed and what is missing. Huawei's Ascend artificial intelligence accelerator line has captured meaningful domestic Chinese market share following NVIDIA export restrictions, according to multiple industry reports and public statements from Chinese artificial intelligence companies. The chips are in use in production clusters. Whether Ascend products incorporate LogicFolding, or whether LogicFolding is a disclosed research direction that has not yet reached production, is not confirmed in public reporting as of the information available here. The density-to-capability translation for artificial intelligence workloads is well established as a general principle. A genuine 55% density gain, if it reaches production at acceptable cost, would represent a meaningful performance step for the domestic market. The cost structure remains the unquantified variable. Round 3 splits. The usability case in a restricted market is real. The cost structure silence in the disclosure is a genuine hole. Award the density translates to capability argument to the bullish side. Award the economics are unproven argument to the skeptics. The round clarifies what is actually being contested, not whether the architecture works in principle, but whether it works affordably at scale. Round 4 is the decisive one, and it turns on what node names actually mean. The bullish argument starts from a factual premise. Node names have been marketing figures since the industry abandoned gate length as the defining metric roughly a decade ago. One foundry's 7 nanometer and another's 7 nanometer were not comparable physical processes. The denser one was denser. A third major foundry's nodes diverged further from physical gate lengths. When a leading foundry calls a process 2 nanometers or 1.4 nanometers, that number refers to a density and performance tier defined by that company's internal roadmap, not to a physical feature you could measure with a ruler under a microscope. Huawei applying 1.4 nanometers to a process that achieves a stated density is doing exactly what every other major foundry does. The naming convention is industry-wide. Criticizing Huawei for using it while accepting equivalent abstractions from TSMC or Intel would be an inconsistent standard. The counterclaim is where the round turns. The inconsistency argument points in the wrong direction. The reason the industry moved to density-equivalent node names is that extreme ultraviolet lithography enabled density gains that 193-nanometer immersion tools could not achieve, and the naming tracked those gains. When a leading foundry calls a process 1.4 nanometers, the density it claims is achieved on a single planar layer, with extreme ultraviolet patterning at feature sizes and interconnect pitches that immersion light cannot resolve in a single pass. When Huawei calls a stacked architecture 1.4 nanometers, the density is achieved across 2 vertical tiers. That means the effective feature size on each individual layer is larger. The interconnect pitch within each tier is larger, and the power delivery and signal routing constraints are fundamentally different. The label is the same. The physics is not. Consider the distinction concretely. A structure that achieves a certain area density by stacking 2 tiers and a structure that achieves the same area density in a single planar layer produce chips with different clock speed ceilings, different power envelopes, and different paths for further scaling. Calling both 1.4 nanometers is not technically false by the current convention. It is accurate and misleading simultaneously, which is the most useful kind of accurate to interrogate. The evidence on this round draws on documented industry history. The transition from physical gate length to density-equivalent node naming is not contested among semiconductor analysts. Independent research institutes have published analyses noting that node names across foundries became non-comparable once the industry shifted its defining metric. If Huawei's LogicFolding disclosure expresses its density claim in transistors per square millimeter, which reports suggest it does, then the comparison is at least dimensionally consistent with how other foundries state their figures. The physical distinction is that the area being measured includes 2 stacked tiers rather than 1 planar layer. Think of it this way. A structure with 2 floors holds more in the same footprint than a single-floor structure of equal area, but the objects inside are not occupying a smaller space. The footprint density is real. The vertical structure changes what you can do with the density. No independent metrology laboratory has measured feature sizes on a chip produced using the LogicFolding method. Round 4 to the skeptics, on the narrower but more important point. The node label is not fabricated. It follows the industry's own convention. But that convention, applied to a stacked architecture, systematically overstates the comparison to a planar extreme ultraviolet process. 1.4 nanometers on a stacked architecture and 1.4 nanometers on a planar extreme ultraviolet process are not the same physical result described by the same number. They are different physical results described by a convention that was never designed to distinguish between them. The distinction matters for anyone using the headline to benchmark Huawei against leading foundry roadmaps directly. Before the verdict, the dissent deserves 3 direct statements, because this ruling is exposed on each of them. First, the yield and cost data may exist internally and simply not be disclosed. If Huawei is producing LogicFolding chips in volume at acceptable economics right now, The absence of published figures does not mean the figures are bad. Undisclosed is not the same as non-existent. A production announcement or an independent teardown would retroactively validate the architecture on grounds the current evidence cannot establish. Second, the thermal constraint on three-dimensional logic stacking is real, but not necessarily permanent. Microfluidic cooling channels, integrated heat spreaders embedded between tiers, and other thermal management architectures are active research areas at major institutions. If Huawei has solved or partially solved the thermal problem in ways not described in the public disclosure, the yield multiplication and heat dissipation objections shrink considerably. The skeptical case depends partly on the assumption that the undisclosed engineering is absent, not on proof that it failed. Third, the node naming critique applies to the entire industry. If this verdict penalizes Huawei for naming a density equivalent node by density, rather than by physical feature size, the same verdict should have been delivered on every foundry that made that transition years ago. The honest ruling is that the naming convention is broken industry-wide, and Huawei used a broken convention in the direction most favorable to its headline, which is exactly what every other major foundry has done. The verdict holds, but the dissent defines its scope. The ruling is not that Huawei fabricated a result. It is that the framework for naming the result was already compromised before Huawei used it, and Huawei used it in the direction most favorable to its headline. Here is where the 4 rounds settle. Huawei demonstrated a real density gain using a real architectural innovation on tools it can actually access. The LogicFolding disclosure is not a fabrication and not a relabeled prior node. It describes a method that, if it yields at production scale with acceptable economics, advances Huawei's position in the domestic artificial intelligence accelerator market in a meaningful way. The skeptics are right on the narrower but decisive question. 1.4 nanometers as applied here describes a stacked density result, not a planar lithography result, and the two are not equivalent in clock speed ceiling, power envelope, or scaling trajectory. Huawei won the density round. It did not win the node round. Those are different contests, and the headline conflates them. The useful question going forward is not whether China reached 1.4 nanometers. It is whether a density equivalent result achieved through architectural stacking can compound over time the way a lithography-defined node compounds. A lithography node scales by shrinking features across the entire planar surface, and each shrink multiplies density and efficiency together. A stacking architecture scales by adding tiers, which multiplies density, but carries thermal and interconnect penalties that grow with each additional tier. The scaling trajectories are not the same. Whether Huawei's architectural detour leads to the same destination as the lithography road, more slowly, or to a different destination with different limits, is the contest that is actually still running. The current disclosure does not answer that question. What it proves is that the export restriction on extreme ultraviolet equipment did not end Huawei's advancement. It changed the direction of that advancement. The restriction that was designed to settle the contest reopened it on different terrain. LogicFolding is Huawei's answer to a question the sanctions asked. The answer is partial. The headline is inflated, and the engineering underneath it is real. The round Huawei lost, what 1.4 nanometers actually means, may matter less in 5 years than the round it won. That density, by any method, keeps compounding. Round 2 is the one this verdict is most exposed on. If Huawei has yield data, it is not published, and the stacked logic economics work at scale, the skeptical case collapses. What specific threshold would convince you that the stacking yield problem is solved? A production volume announcement, an independent teardown, something else? Leave the specific threshold in the comments, because that disagreement is the most productive one this analysis raised. If the rounds here changed how you read the next semiconductor headline out of China, the next analysis lands on this channel. Subscribe and turn on notifications so it finds you when it drops.